Hello and welcome to the Gen Chem 2 laboratory exercise on antacid analysis. So we know antacids from our regular lives because they're used for acid relief of an upset stomach. Your stomach releases hydrochloric acid in order to break down your food. So the more foods that you eat that contribute to the acidic environment, the more uncomfortable that you will feel as you continue to eat them. This is a primary reason why many of the foods in the Western diet actually cause an upset stomach. So this leads to circumstances known as heartburn and indigestion, and so we frequently will buy what we call neutralizers over the counter in order to relieve the condition. Now, there are several types of ways to neutralize acids in your stomach, and they all have different ingredients. We have our calcium carbonate. We have our milk of magnesia, and then they are a series of then there's sodium hydroxide, which will neutralize it immediately. But most of your commercial brands involve establishing what's called a buffer system, where as acid is released, it consumes the antacid and burns away as you continue to eat it. Now, the television commercials claim different fidelities for these. We're also going to look at today in lab sodium bicarbonate, because that's also baking soda used to eliminate acid, and it stops a lot of reactions actually. So this is actually, we're going to show you that this is, even though it's unappealing and unappetizing, it's one of the major ways in order to neutralize acid. As we do the analysis, you will notice that when we compare brand names to baking soda, we have to look at how much acid is neutralized per gram of antacid. When we're looking at baking soda, this is typically sold in pure form, but most of our brand named antacids are an amalgamation of different ingredients. In particular, we're going to pay attention in this lab to one that has no color in it, because the color of many of these antacids actually interferes with our analysis in this experiment. So the one I chose for today was chosen specifically for the fact that the pill is clear or white, and ergo there will be no artificial dyes or whatnot to interfere with our reading our results in lab. So there are three different reactions: the carbonate reaction, the bicarbonate reaction, and the hydroxide reaction. And what they all do is they create a buffered system with water, and it causes a secondary equilibrium. So because of what's released in terms of most of the brands which contain soluble carbonates in order to neutralize acid, what they will do is they will release carbon dioxide gas into the system, which combines with water in your cells to create an equilibrium of sodium bicarbonate, or carbonic acid, which is present in your cells. This is an acid, and so it's also not ideal, so the acid won't actually be neutralized. So in order to make it effective, if we're going to use a carbonate containing antacid like we are today, the one we're going to be using contains that, both Tums and Alka-Seltzer, hence the term seltzer water, carbonated water. Both of these contain carbon dioxide, so we're going to have to heat them in order to dry this off. Because remember, we learned from Le Chatelier's equilibrium that acids are temperature dependent, and so as we heat it, what it's going to do is it's going to drive the gas off, and this will be evolved out, and it will burn up all the carbonic acid that remains. We also have to do this in the case of baking soda, because baking soda also contains will facilitate the carbonate and carbonic acid buffer system. And so whether we're using baking soda or these two brand names, we're going to have to heat them in order to drive off all of this secondary acid that we create as a consequence of adding it to the acidic environment in our cells. So for purposes of today's experiment, we are going to take, it'll be two parts, so I'll go ahead and draw them all up front. And you'll need at least 2 samples of each. One of the reasons for this is, as we've discussed in previous labs, that we want to talk about our precision and lab technique. And so we want to make sure that we do things in replicate in case we come up with what's known as an outlier. You may have to do a third one, but you're going to do at least 2 times. The third one would be necessary if they're not consistent, if they're not close, because there are many things that can contribute to this, but you won't know necessarily unless your starting weights are exactly the same, how close they are, until you do your math. Okay, so what we're going to do is we're going to put in 25.0 milliliters of simulated stomach acid into all of these Erlenmeyer flasks, all 4. It's a dilute concentration of 0.100 molar HCl, which is approximately the concentration that is found in your stomach if there's no food in it. And then to that, we're going to weigh out about 2.25 grams of baking soda into the first 2, and then we're going to grind up a Tums tablet, and we're going to add about 0.40 grams of Tums to that solution, and add an indicator, which is used in order to help us visualize once the neutralization has actually occurred. And this, in the case of this experiment, this is methyl red. Okay, methyl red is red in the presence of an acid. So once you've added this, these will not neutralize, they should not neutralize all of the acid, so it will still be red. And then what we're going to do is we're going to titrate all of these examples with a dilute standardized 0.100 molar sodium hydroxide. This is in order to determine how much excess acid remains after the tablet has been added. And what we're going to do is we're going to compare these two to compare their neutralization, because the one that leaves the less remainder would be the more effective antacid. So we're going to use fewer grams of this and greater grams of this, again, because the Tums contains inert ingredients, colors, fillers, binding agents. So we found by measuring these before that in order to approximate the same mass of actual neutralizing agent, we need to have a larger amount of starting pill. And you'll find this is true for almost all pills that are sold over the counter. They're not pure substances. So in order to get the same number of moles of neutralizing agent, we need a higher number of grams. And then we're going to compare per gram the neutralization capacity based on which one of these leaves less acid remaining after the neutralization has occurred. Alright, so you're going to, in order to find out how much acid has been neutralized, you're going to, the total acid, which we had at the beginning, which we used this volume and this mass to calculate how many moles of HCl, is equal to total minus, the neutralized HCl equals the original HCl minus the remaining HCl. Okay, so we know the original HCl from in terms of moles, from our volume and our concentration from the bottle at the beginning. And we're going to calculate how much remains by a titration. So subtract the amount that was remaining from the amount that we know we started with will give us how much was neutralized. Then you put that over how many grams of antacid, and that will give you the neutralization capacity per gram, and you can compare those to one another. Okay? So you will add dropwise your sodium hydroxide, goes in the burette, and we'll be putting that into our Erlenmeyer flask, and just dropwise in until it shifts from red to, it'll go to clear first, and then once you have put in too much, it will go to yellow. And so it's red in an acid, clear at the neutralization point, and then slightly yellow once it's shifted to a base. So you'll dropwise add your sodium hydroxide until the color changes, and at that end point, the concentration of acid times the volume of acid is equal to the concentration of base times the volume of base. So we know the volume from up here, we know the concentration of acid from up here, we know the concentration of the base from here, and we're going to measure the volume of base that we add in order to plug into this. Okay. What we want to do is have the volumes for the base that was required be approximately within 5%, and then compare and contrast whether or not our runs are consistent. And if the runs are not consistent, then it would necessitate an additional trial. Again, this will depend on whether or not your initial mass is the same, and whether or not your titration ability. Not all pipettes are created, or not all burettes are created equal, and so some of the tips deposit liquid at a greater rate. Some of the stopcocks right here are also difficult to work, and so getting this exactly perfect requires a little bit of skill and may not actually be within the realm of possibility without a lot of extra effort. Okay, so that concludes our lab discussion for antacid analysis. We'll be simulating some stomach acid, adding an antacid to neutralize the acid, measuring how much acid remained after we added the neutralizer, and then comparing the buffering capacity of one to the other. And so you'll be calculating that today based on the videos that you watch. Good luck in lab, stay safe, and buy wisely. Good. All right, welcome to the commercial antacids lab. What I've already done is taken the liberty of dispensing some of this simulated stomach acid into these 250 ml Erlenmeyer flasks. In these 5, I've already added the methyl red dye. I'm just going to add the 4 drops to this one so that you see that that's what I did. And what we have put is 50 mils of our 0.100 molar hydrochloric acid stomach acid, and then we have added the dye that shows the color that we're going to be using to measure our color transition. Okay, so I set some of these aside for our antacids, and then the first 2, what we're going to do is going to add some sodium bicarbonate that we're going to measure on the balance, and then put that into here, and then make sure that we have enough acid so that there's an excess of acid.
Pause.
Alright, so we've already tiered our balance to 0 and got our weigh paper on there, and we're going to get 2 samples here of baking soda, and we're going to try to get about 0.25 grams. And of course, I did them both at once. We're going to call that good. All right, so that's our first sample. I'm going to put that in the Erlenmeyer flask that's labeled B, because that makes sense. And then we'll prep our second sample. Okay, so that'll be our second sample as soon as we get it to stop oscillating. Okay, record your value. And then we'll put that in the Erlenmeyer flask marked C. Alright, so we've dissolved our sodium bicarbonate into our simulated stomach acid here. And we want to make sure that it has not changed to a yellow color. If it's changed to a yellow color, then all the acid has been neutralized. And as you can see from both of these, they seem to be retaining their color as presently constituted. So this is a multi-part reaction, so the next thing we have to do is put these on the hot plate to drive any carbon dioxide off. That will allow the reaction to continue to proceed. We want to make sure as they are warmed that they also don't change to yellow, because that will again indicate that we have neutralized all the acid and there won't be anything to titrate. So while we have those boiling, we're going to go ahead and set up the antacid, which is done the same way. Before we measure, again, I have these Erlenmeyer flasks. As stated before, we've measured by pipetting 50 mils of our simulated 0.100 molar hydrochloric acid, stomach acid, and we've added our indicator. So next we're going to go measure some of our Tums into this, and then we will continue. Alright, so what we've done is we have ground up one of these regular Tums tablets using our mortar and pestle. And we're going to measure 2 samples out of approximately 0.4 grams each. So this is our first one. One of the reasons we need a little bit more of our antacid tablet than we did of our sodium bicarbonate is because there's some binding agent that's inert in each of the tablets. So we need a little bit more in order to achieve the same neutralization capacity. Of course, I laugh, so it's not quite. All right, so record your mass for that one. And we're going to put that into the Erlenmeyer marked A. And then prep our second sample. Whoever designed a mortar and pestle obviously designed it with these scrupulas in mind. And record your mass. And we'll put that into this Erlenmeyer flask here that's marked with the letter C. Okay. All right, as with our previous samples, we are going to dissolve these in here, making sure that they have not changed to a yellow color yet, because that would indicate that the Tums tablet that we added had already neutralized all the acid in our Erlenmeyer flask. So once they are dissolved, we're going to then put these onto our hot plates as well, and then get our titration ready. This is A and C. All right, now for our titrations, we have these burettes that we have filled with our standardized 0.100 molar sodium hydroxide solution. So we've already gone ahead and filled them, and we need to measure, first of all, our starting points. So for your starting point, still running, right? Okay. All right, so when we look at our burette, we are looking for the initial reading here in the top of the burette. In order to read it, sometimes you have to put a reference behind it. So for this titration on this side, you read at the bottom of the meniscus in the burette and take your reading of your initial volume for this particular burette. For the one on the right-hand side, again with our contrasting background at the bottom of the burette, you can indicate your initial volume for the burette. Burettes are designed in order to measure how much has been dispensed. So we're going to have a starting value and then a final value, and the final volume minus the initial volume will be the amount of titrant that it took in order to neutralize the acid in our Erlenmeyer flask. So by subtracting those two numbers, we know the volume of sodium hydroxide that it took. So we're going to keep boiling these until we have driven all the carbon dioxide off. And then once we are finished with that, we will proceed to the titrations. All right, as we can see from our Erlenmeyer flasks here for our sodium bicarbonate, they have proceeded to boil, and they have not changed to the yellow color, so we are good to proceed. I carefully remove them from the heat and allow them to cool. As we talk a little bit more about burettes, I'm going to rinse down the sides of these really quickly to make sure that if there was any acid that came up, we incorporated into the volume at the bottom of the Erlenmeyer flask. Adding excess water, since water is already neutral, will not change significantly the amount of titrant required. So they're still pretty warm. Okay. A couple more comments on the burettes. Once we have filled it, we want to make sure we turn the stopcock here and let a little bit pass through to make sure there's no air bubbles here inside the bottom of the chamber. So I've already filled them and then drained them a little bit, so there's a little bit of liquid down in here that I collected under the bottom. So we'll put these under here and get them ready for, of course that's not high enough, because of course not. Chemistry is taught in front of a live studio audience. Okay, the way titration works is we carefully add our titrant, which is our 0.1 molar sodium hydroxide, to the Erlenmeyer flask with a swirling motion until we reach the end point, at which point we will see a color change from whatever this is to the yellow, indicating that all of the acid has been neutralized. We need to begin our titrations now. It's like watching paint dry. And because we're titrating with the base, we want to make sure we're properly safe wearing our PPE, especially our goggles, because the last thing you want to do is have to tell people you got hurt in chemistry lab because you were dropping the base. Going to keep adding it dropwise until we reach the end point, at which point we'll see a color shift to yellow, and we'll stop the stop cork and take a measurement of our final reading. Because the masses of these are both very close to each other, we should get the exact same volume, more or less, for our titrations. That will show whether or not our precision has been good, and you'll be required to comment on that in your lab report. Do you know what the volume is, Mark? It's supposed to take.
Not sure.
Just think, depending on what job you get, you could be doing this for a living, like me.
James can play this by 40x or something. Because it's taking, I think it goes into almost the 40, because 10% of it will be neutralized.
I know the bike takes more because it's more effective. Those are not as much.
Oh yeah, so this could be in the 30s then.
It's getting close.
That's good.
Okay, so we can see from the color change, we have eliminated all of our initial color, which indicates that the acid has been neutralized. We'll go ahead and do this one, then we'll take our burette measurements. So now that I know approximately how far. And because we know that about the same mass, we'll do the drops a little bit faster than this one. Alright, so we've eliminated our color from both of them. So we're ready to take our burette readings. Sorry, I lied. Gotta move this one more time. Okay, so we look at this is our first burette reading for the Erlenmeyer flask labeled B, which was our first sample. And so you look at the bottom of the meniscus and take your reading. And then this is for the Erlenmeyer flask labeled C, which was our second sodium bicarbonate sample. And boy, it's hard to see this through goggles. So do your best to take a reading at the bottom of the meniscus from that. Okay. Go ahead and pause it. We'll set the other ones up. All right, now we have our TUM samples here. So we have sample A and sample C. What I've done first of all is I've refilled our burettes so that we can take our measurements. So the first thing we've got to do is record our initial volumes like we did before, after you got all that nicely set up there. Okay, so this is Erlenmeyer flask A, or sample 1 with our TUMs. So reading the meniscus, take your initial volume. And this is our second sample of TUMs, Erlenmeyer marked C. And reading the meniscus, get your initial volume. Okay. So we'll go ahead and get that set back up. And then again, as before, we're just going to add this dropwise until we see the same type of color change. These particular tablets, because they were uncolored, you won't have a masking agent. Sometimes if you have a colored or like mint Rolaids, it will also cause another color change, so I try and stay away from those because then it makes it harder to compare to our outcome with these previous samples. And because this is a different kind of agent and we don't know exactly the composition of our TUMS tablet, we're going to be meticulous in making our measurements. And I'll shut up so we can speed this up. I guess I can talk and we just pretend that it doesn't matter. Should have been an actor. I'll tell you why that's funny in a moment, cause this one is sticking to the platform. I don't know why. this is the one that takes 40.
Yeah, because it's
not-
usually the neutralizing capacity is only about like 10%.
I know it's not as good as sodium bicarbonate, but it's all I can remember for sure. Plus, it sort of depends on what mass you started with, and I started with lower masses so that this would take as short of a time as possible. I learned that from my TA in Gen Chem 2, which I took as a senior, because I tested out of the lecture. Okay, we have completed our color change for sample 1, and as you can see, it's a little bit different, but we have ablated all of the color agent that was in there, so we know we've reached our endpoint. So we'll start the second one. And it's about the same. That's interesting. All right, we have now completed both of our titrations and eliminated the original methyl red coloring agent. So we're going to take our final burette measurements, and then I'll make my final comments before you move to the data calculation section. So this is the Meyer A, and our burette reading you can take from the meniscus. Okay, it's focused. Okay. And remember, because that's above 19, it's slightly less than 19. Pro tip. And this is our other sample, which is Erlenmeyer C. And take your measurement from the meniscus there. Okay. And that concludes the data collection. Now, one of the things they're going to ask you to do once you've done all your calculations between the bicarbonate and the TUMS is to think about and calculate the relative neutralization capacity. To think about why we take these and don't suck down sodium bicarbonate to neutralize acid when we have an upset stomach. Remember, as you consider that, to consider not only the volume of titrant required, but also the mass involved between the two assays with our sodium bicarbonate versus our TUMS. Different acid neutralizers will also have different efficacies.